Okay, we can start. Good afternoon, everyone. Thank you for coming, both people that are here and people connected through the webinar. Today, this is the 8th appointment with the ReStructure 2.0 webinar series. I'll give you a brief introduction why we are here, what we are doing. First of all, what's ReStructure 2.0? ReStructure is a research project that is based at the Department of Civil Engineering on the University of Calabria that was funded by the European Commission using the Marie Sklodowska-Curie action, in particular the integration panel. Why there is this, we are here today. I decided to start a ReStructure 2.0 webinar series that is basically an appointment that we make often to create an active network in which discuss about topics that are from the broader area of geotechnical earthquake engineering, but also, as you will see today, from some useful tools that we can use to enable this research. And then, of course, to disseminate research. This webinar will take place almost every month. They started last January and they will go through August 2023 until the project, when the project will end. And this webinar will be in person here at University of Calabria, but there will always be a connection through the team channel of the project. What will be the presenters? I decided to call the presenters about the whole world, so the geotechnical earthquake engineering world. But so here are some of the speakers that already have been hosted in this webinar series. But today we have Dr. Tim Cockerill from the Texas Advanced Computing Center. And how to be informed to know about this webinar series. There is a website for the project as well as a newsletter. And once you sign up, you will receive all the appointments, the news, and the important things about the project. And then, of course, there are like social media channels related to that. I just want to spend few words about like the supercomputer, today's presentation. As I told you, the presenter is Tim Cockerill. And Tim Cockerill is a TACC Director of User Services. He oversees the allocation process by which computing time and storage is awarded on TACC APC systems. The user service team is also responsible for user account management, training, and user guides. Tim also currently serves as the DesignSafe Deputy Project Director, providing a web-based platform supporting natural hazard research. Tim is co-PI on 2 NSF CC awards, providing training and research support for underserved, under-resourced universities and community college, and is also a co-PI on an NSF Office and Advanced Cyber Infrastructure awarded for an innovative prototype APC system known as Texas A&M University. Tim joined TACC in January 2014 as the Director of Center Programs, responsible for program and project management across the center's portfolio of awards. Prior to joining TACC, he was an associate project director of XSEED and the TeraGrid project manager. Before entering the world of high-performance computing in 2003, Tim spent 10 years working in startups company aligned with his research interests in gallium arsenide materials and semiconductor lasers. Prior to that, Tim earned his bachelor and master and PhD degrees from the University of Illinois Urbana-Champaign and was a visiting assistant professor in the electric and computer engineering department. I want just to add something. The reason why Tim is here today, because before coming back in Europe and at UNICAL with this Marie Curie Fellowship, I had the privilege to work with him at the Texas Advanced Computing Center. This was a great experience for me, helped me to learn many of the skills that I couldn't have that I put into the project. So I'm really grateful to be able to work with him and to call him a friend and to have him here today that is visiting Italy and he was able to make it. So thank you, Tim, for being here and for accepting to be here for the seminar. And I'll just give this to you and I'll just open your slide. Thank you.
All right. Thank you, Margot. I'm used to standing up and walking around, so I'll probably move around in my seat a little bit. Hopefully I won't be too distracting, but I'm so pleased to be here and I thank you for the invitation to come And I'm really looking forward to telling you about the future of high performance computing at the Texas Advanced Computing Center, which is the leading high performance computing center in the United States. So we are doing a lot of cutting edge things, but we do so much. It's not really about the computers, it's about your research. It's about the world's research, and the National Science Foundation encourages us to do international collaboration. So I want to make sure the main thing I hope you take away from this is that we can work together. We do work together with many people around the globe today, and that many of these resources are available to you through collaboration, and there is no cost to you to use them. So if you can just take that away, I'm not here to sell you anything. I'm here to help. Okay. So I work for the University of Texas at Austin at the Texas Advanced Computing Center. You'll see my shirt says DesignSafe. Margot talks a lot about DesignSafe. That is a project that we have. So, but we are part of the University of Texas. We are University of Texas employees, and that's the most important thing. We are not a private company. We are a department at the university, and our job is to enable you to make discoveries using computation and computing technologies. That is what we do. We do some research ourselves, but our main priority is to support everyone else's research. So if I'm going to talk about the future of computing at TACC and the National Science Foundation, I should talk first a little bit about the history of TACC. Prior to that, being at the University of Illinois Supercomputing Center in 2003, and I moved to TACC in 2014. NSF Supercomputing, National Science Foundation in the US Supercomputing, started at the University of Illinois in 1986. I joined that institution in 2003. And a couple of years before I got involved in supercomputing, the University of Texas decided that their local research computing, and you have local research computing here, was going to try and go larger and be part of the national supercomputing effort. And you have to write proposals. They're very competitive, and you have to win awards to build the next big supercomputers. In 2001, TACC started with a small number of people. And what is a small budget? 12 people, $600,000 a year. They had a 50 gigaflop computer. Today we talk about petaflops. So the original system is about 1/200,000th of what we're producing today. If you have a smartwatch, you probably have much more computing power on your watch than we did in this Cray supercomputer, right? So that was 2001. 22 years later, we have nearly 200 people, about 70 of us have PhDs. This is why we can help you. Many people at TACC, especially PhD level people, were computational researchers themselves. And then they decided they wanted to help other researchers and continue to work at a university. And they're from many disciplines of science: astronomy, biology, physics, chemistry, engineering, economics. And they wanted to help other people do their science. They work for us now. We have a very large data center that has 12 megawatts of power on a daily basis. We typically are drawing 9 megawatts of power when all of our supercomputers are up and running. We have multiple supercomputers. 8 billion compute hours per year. Okay. We have a lot of capacity. Again, funded by the National Science Foundation. Almost all of that is. A little bit from the University of Texas. Billions of files, petabytes and petabytes of storage capability, and multiple systems. Frontera is our current largest system. Stampede 2 We'll talk about on the next slide a little bit some of the sizes of these systems. And it's to let you know that we have what is essentially unlimited capacity to most researchers. We support a lot of researchers as well, and that's another point I really want to make. These systems are not just for the very largest users of computational time doing the very largest simulations. They work with us. They use our systems. But we have over 15,000 people who log into the systems and use them any given year, over 4,000 projects, okay? So some of those people just need something a little bigger than their laptop to do their work. They can come to us and do their work, okay? We have people that use 2,000 servers at a time to do one single job. We have somebody using one. That's okay. We support all of that research, and we want to. Our people. That's really what makes us special. It is not, the hardware is great. It is wonderful hardware. But the most important aspect is our people, and we can help you. Here's some images from inside our data center. On the right, this is our current large system, Frontera, our most recent system, and it will last, it's been online about 3 years. It will last another 2 or 3 years before it's old. You know, an HPC system is old when it's 5 or 6 years, and then there's new technology that's going to be probably usually at least 2 times faster, more capable, and I'll show you in a minute that we have to now be 10 times more powerful in the next one. And it's not just meaning 10 times more servers. There's much more to it than that. Over here with all the bulls running, this is Stampede 2. And if you look real close, those are real horns from a Texas Longhorn cattle right there. This is the mascot of the University of Texas. It's the Texas Longhorn. So we have a lot of fun. Our graphic designer has a lot of fun. This is a air-cooled machine. So there are tiny holes. This is not vinyl. This was painted onto the doors by someone who custom paints motorcycles. We approached him and said, "Would you do this?" And he said, "Sure, that sounds great." And then he did it. And he came to look at it because he did it one door at a time in his little shop. And he came in to look at it and he said, "That is amazing. I can't believe I did that." But he had to poke the holes out of every little hole in the door so the air would flow through. He said, "I love it. It's beautiful. Please never ask me to do one again." So what do we have? What are some of the particulars, right? So like I said, we have a lot of resources. We have over 18,000 servers in our data center, which amounts to more than 1 million computing cores, right? Nowadays, processors are multi-core, right? When I first started in this, one CPU meant one processing core, right? Now, even in your laptops, right? You're typically your computer, your laptop has 8 processing cores at least in it, right? Mostly funded by the National Science Foundation. The equivalent, if you had to pay for this through Amazon or Google Cloud or IBM, Microsoft Azure, they would charge you something like $300 million a year for that amount of computing time. My budget is not $300 million a year. You know, it's already paid for by the National Science Foundation, but our budget is more like $40 or $50 million a year. So there's a lot of value in working with us because you not only buy computer time, because when you pay $300 million a year to a cloud company for that, you don't get user assistance. You don't get somebody helping you. You don't get a researcher who did computational research helping you with your research. We do that. That's the biggest part of our contribution. So Frontera is our big system. Whoops, let me go back. Is it down here? Just right there. Stampede 2, with the one with the cattle on it, was also our big systems, right? Our second largest system. It's getting very old. It's 6.5 years old now. They keep extending it because they don't have another big system yet. And then Lone Star 6, which you see part of here, is funded by the University of Texas. And then we have all these other things. Some of them are storage systems. Some of them are specialty compute systems for computer science, cloud computing, that kind of thing. This peculiar looking box holds servers in mineral oil, completely immersed. So today, AI is a very big thing, right? GPUs are very powerful, but they're all and they're very much utilized in AI, but they also produce a lot of heat. Mineral oil is non-conductive, and so we take the fan off of the server, right? Normally they're air-cooled, right? We take that off, and we do some other specialty things to make the connectors not leak, and we drop the servers, and they're constantly immersed in mineral oil, and they run much cooler that way, because you have direct contact to remove the heat from those boards. And when we do that, we only have to cool the oil a little bit. When we direct water cool, we have to cool the water much more. And when you do fans and air cooling, the air has to be very much colder than your target temperature, because you have very inefficient cooling with air. So it costs us a lot less money and a lot less energy to do this. So while we run 9 megawatts of power in our data center, we try to do several things so that we're not running at 12 megawatts. Okay, we do reduce our energy footprint as much as we possibly can. You know, just the reminder, how much does it cost me to access your computers? And yes, I hope you will like the answer. It doesn't cost you anything because it's already paid for. And it's not just using time, it's our people too. You don't have to pay to get help from our people. You don't have to pay. There are international collaborations, as I said, welcome, and there are multiple ways to make those connections. I'll talk more about that as we get to the end of the presentation, and my slides will be available, and you can reach out and get them. I hope that you will be able to, in the future, if you have needs or you want to do something, please refer to these and find ways to talk with us. As I said, the National Science Foundation encourages us very much. So Frontera has on nearly 8,400 compute nodes or servers, right? We had 50 gigaflops, right, 20 years ago. Today we have 40 petaflops, right? 200,000 times more computing capability in a single computer. A lot of petabytes of RAM, dozens of petabytes of what we call scratch file system. That is the working file system where, when you're working on the computer, this is where your data is being written to and from, and it's very fast parallel file system. If you have a lot of data you're moving around, we have a separate flash memory file system for that, and that fast interconnect is running at 200 gigabits per second per channel, and it's a parallel file system. Okay, so we can move a couple of terabytes per second of data around if you need to. Intel is the most predominant processor in our facility, and so you'll see a lot of that from us, but we also have AMD processors as well on some of our systems. Normal production, any user that has access to our system on Frontera can run up to 2,000 nodes in a single job. And then we have special, and that's more than 100,000 compute cores, right? 56 cores per node, 2,000 nodes. We have special days, Texas scale, everything's bigger in Texas. I didn't grow up in Texas, but when I started working there, I realized what they meant by everything's bigger in Texas, and they're very proud of everything being bigger in Texas. I'm from Illinois originally, and I now live in Alabama, actually. But anyway, Texas, we call these Texas scale runs, right? Exascale, as after petascale computing, petaflop computing is exascale is the next, right? Exabytes, petabytes, exabytes. So we call it Texas scale runs. So we set aside a week every quarter for the largest jobs. And these are people who can run a simulation on all 8,000 nodes. One single job, 8,000 nodes. We give them 24 hours at a time. We have 4 or 5 research projects that do this, and they run jobs that do some research that has never been done before at a scale never imagined before. And they have this opportunity to do that. On a daily basis, we can't do that. We have to support the small to large jobs. And so this is what we do, is we run these special jobs for a week. And we call them Texas scale jobs. And it is mind blowing to think that somebody runs a single job on 8,000 nodes of a computer. We do have a lot of GPUs around. Frontera has 360 GPUs. And then Lone Star 6 is our most recent computer that has a smaller amount of nodes, 560 nodes, with 2 of AMD's most powerful new processors. They're 64 core processors. Each node then has 128 compute cores. If many researchers can get a lot of work done on a single 128 core job, right? You can run 128 threads, 128 processes at a time through here. GPUs on here also, we have 80 nodes times 3, 240 GPUs per node. And these are NVIDIA's currently most capable and fastest processors, although we will soon have the H100, the Hopper GPUs as well. We get access to all the new processors, accelerator cards, all the latest technology we get to test in our facility because we buy so much compute hardware from these vendors, and we test it at a scale never before seen when we deploy our big systems. So they're always wanting to give us the newest hardware because they think more than likely we're also going to win the next big award. We have a lot of different ways to approach data, and that's because one single way of approaching data storage doesn't meet all the needs. So when you're on a computing system, on one of our supercomputers, each server on the supercomputer, you can store some data locally, right? But that data you need, you have to move it off of there before you're done, right? And we actually wipe the nodes at the end anyway when your job is done. But you can store some things locally on each server when you're running. Mainly, you're going to work out of what we call the scratch file system, and it's shared by all users on an HPC system. And our systems usually have upwards of at least 20 to 30 petabytes and upwards of 100 petabytes of capacity because you're sharing this across several thousand users. So we need that much capacity. And this is where, and that's the one I said earlier is very fast connected at 200 gigabits per second. We have what we call the work file system as well, and everybody gets 1 terabyte of storage. You become a user, you get a terabyte. That's it. Just by being a user on our systems, you can store up to a terabyte there. We don't actually back that up, so if you needed to, you can do that yourself or to our tape drive down here at the bottom. But this is a place that lives in our data center, and it's the same file path. It's mounted. That file system is mounted on all of our big supercomputers. Otherwise, if you're working on Lone Star 6 for a little while because you wanted to use their A100s and then you needed to run a 2,000 node job on Frontera, you'd literally have to transfer the data across. That takes time, especially if you're talking about terabytes of data. The work file system is mounted, meaning that the same file path for any system you're working on, it's just attached. And so it just can grab that data very easily. DesignSafe and other big projects are use a storage system called Cockerill. This is still a disk storage system. It's 50 petabytes, but it is a slower, we can spend less money, slower disk, and slower network attachment to it because you're not going to work your directly out of here and send data directly to a compute node. you would have to transfer data from here over to one of the supercomputers to use it. But it's great for data collections. And we have all kinds of data collections in Cockerill. We have data collections on butterflies and fish and all kinds of things, all the way up to some astronomy projects. Arecibo in Puerto Rico, the big telescope that had been around for decades, collapsed a couple of years ago, right? And so all of the data from Arecibo is coming to Cockerill. There's a problem with bringing data from a remote wilderness of the very end of the main island of Puerto Rico. Is there's no internet. There's no good internet there to move terabytes and terabytes of data. They are literally putting it on disks and bringing it to us, and we're bringing it, and we do that too. So, and then we still run a tape archive. Tape has been around forever. In the beginning, that was how you stored any data, and that was how you transferred data. And if you've ever seen old movies of the spinning tape and everything, right? That's how they do it. Today, it's cartridges and robots, and we have currently over 200 petabytes of data on tape because we keep everything. Everything that a user decides they want to keep. But we don't throw out any old data. When we bring in the newest tape technology about every 8 to 10 years, we keep all the old data. And in fact, I said, we started from the University of Texas Research Computing. We have the data from the beginning in 1986 when the University of Texas Research Computing started all the way through today. Now, the 1986 data, which was a lot back then, is hardly a blip. You can barely see it in our 200 petabytes, right? It's maybe a gigabyte of data, and they thought that was a lot, right? So, but we have not lost any data in all these years, and if users want to put any data on tape, they can do that. It's very cheap, very inexpensive to do tape, and then people store that there. Okay, what is the future of computing? Where are we going? What is this leadership class computing facility, and why are we doing it? How did TACC become the people selected to do this? Well, Frontera is our current big system, right? But when we won that award from the National Science Foundation, we also won the opportunity to propose to the National Science Foundation the next thing, which was the leadership class computing facility. This is very different. In the past, NSF really bid these computers out as research awards to just like if your research group wanted to study something and you needed funding for grad students and you got $30,000, these were just $10 million, $20 million, $60 million research awards. And they had a budget and you wrote to that budget. We are now moving into the area where things like Arecibo and the big astronomy projects are funded out of NSF, and this is called the operations part of NSF. And computing is finally moving into where it belongs. We're a support service for funding or for supporting all research. And so this is a multi-year, multi-phase process. It takes 3 phases of review. We had to write 3 increasingly complex and difficult proposals that we had to get through these proposal phases. They give us some funding actually to write the proposals because it is so complex, and we have to have project management consultants help us out, things like that. But you start with a concept and you build a budget. And the concept, they tell you, we have to be 10 times more capable than Frontera with the next one. Usually the next computer is 2 to 4 times more capable. At the same time, we're going to be able to get 3 times more money for it. So Frontera was 60 million, and we came up with a budget of around 200 million for the next computer to fund the computer itself. After the first two proposal phases, we successfully got through each of those. The National Science Board in the United States approved our funding level for the construction of the facility at a total of $600 million. We have to get through one more phase, the final third phase of the proposal process. Those documents will be submitted within a month. We believe we're on track to get approval for all of this. And so we expect, as long as the United States Congress, we have to wait on them, and we'll see how that goes. They aren't always very efficient, but we'll see. This is recorded, isn't it? All right. Well, that's all right. Everybody knows. And then the money can flow. This is not part of the standard budget of the National Science Foundation. It takes an act of our government to give us the $600 million to build this out. But we hope to be starting that soon. It will go in this facility, which is being custom designed for us. This is actually not at the University of Texas. It's too much for us to handle in terms of building the power infrastructure and all that would be needed. It will be on the Dell computer, the company, Dell Computers campus. However, it will have our logo on the Leadership Class Computing Facility and the National Science Foundation logo on the side of the building, and will be next to other data centers. But Dell Computer is about 6 miles away from where our offices are today, so not very far. What is the future of computing? Many of you know today's current future is AI, right? I read a lot of proposals for time on our systems, and I'll bet you at this point in time about 50% of them are saying we're going to do at least some of the work we're going to do is AI, right? Everybody's wanting to do AI, and that's great. There's a lot of interest in AI, and it can do a lot of very interesting things for you. It's not replacing traditional modeling and simulation. It works nicely in conjunction with it in some instances. But there is a lot of value in looking at AI and using AI, and most AI does a lot better, a lot faster on GPU computing, especially when it comes to the training of these data sets. I'm trying to look through here. I have a lot of slides, and I don't want to take up too much time. But the big things to take away from this, we have capacity. We have experts at TACC who still write papers on AI research itself, on how to conduct AI research. We give a lot of presentations. We do training, and I'll show you at the end where we have some of that training readily available to anyone in the world. And we have data sets as well that can help you get your training sets done a lot faster, and Margot can attest to that. She's our current GPU resources, in addition to Frontera and Lone Star 6 that I mentioned earlier, we have Maverick and Chameleon. We've got some NVIDIA DGX boxes. We will continue to add additional GPU nodes. A majority of our nodes are standard CPU, as you saw on Frontera. There's over 8,000 standard CPU nodes. Most modeling and simulation analysis codes simply need CPUs. They cannot take advantage of GPUs, or they would be so costly in the time it would take to convert their applications. CUDA programming to run your applications and your simulation modeling on GPUs is difficult still. It's not automatic. It's not easy. Certain kinds of math work very well on GPU. Molecular dynamics codes like NAMD, GROMACS, things like that run nicely, parts of it. But you take the math that really works well on the GPU and you offload it over to the GPU. The CPU keeps running and doing some jobs and work, and then it has to come back. As long as that's running 100 times faster or so over here, that's great. You send that work over, it comes back. But if you take 10 lines of code that you were running in CPU, it's about 200 lines of code to run it on the GPU, and it's very complex. We are just finding, we're not professors, any of us at TACC, but we do teach some 4-credit courses on the UT campus. And this fall, after doing GPU computing for a very long time and supporting it, we're doing our first class teaching CUDA programming for GPUs. So it's a lot. And as was speaking with Leonardo earlier, the Department of Energy has committed to all GPUs, but they also put $1 billion into the software development to convert all their codes over. So the entire NSF budget is $8 billion a year. So we don't have the money to convert everybody's codes over to GPU. We will help people that have an interest, and that's fine. Training and data sets. That is the biggest issue in AI, right? Do I have enough data to have my training set be useful for me and to get good results when I'm actually trying to use this for an application? Where do I find all this data that I need? Well, I mean, if you have simulation codes that you're working with, you can generate your own large data sets, right, that you then use for training. What we've been able to do because of the DesignSafe project, which I will get into more detail in a bit here, is we bring together lots of data sets from around the world as people are willing to publish and make available for others to use. And they're searchable. You can find data. If you do research on reinforced concrete, you can search on reinforced concrete in DesignSafe, find a lot of data sets, go through them, determine if they're of value to what you're doing. And we actually had someone do this several years ago. Well, this Margot did too. And which is why we've worked together. And she's not the only one. We had another researcher at Texas A&M University who I'd never heard of, never worked with, just like Margot. And then we find out they at a conference, I used DesignSafe and I found all these data and I did machine learning. And we're like, we never heard of you. You didn't have to ask us questions. You didn't have to ask us where the data is. You just did it. Thank you. It works. So in addition to DesignSafe for natural hazards research, as I mentioned earlier, Cockerill stores lots of data sets. And in that 50 petabyte data store, we currently have over 35 petabytes of data on a variety of topics. And as I said, butterfly migration, cancer genomics, the James Webb telescope, the most recent images of the James Webb telescope, the new telescope that's out there. We have data available for people to access. And as I mentioned, the most important thing we do really is our people. In the beginning, when TACC had 12 people, most of them were working on supporting the hardware. And they also had to do a little bit of user support, but they barely had time to do that. Now that we have 200 people, we have less than 20 people that work on the systems. Less than 20 that maintain that hardware. We have lots and lots of computer hardware and separate computer systems. But through automation, and we build a lot of our own tools as well for that automation, we have not had to hire. It was nonlinear, right? It was sublinear. We did not have to keep hiring that many people to run the hardware. We were able to hire people to help researchers. And that's been the most important thing that we've been able to do. And the National Science Foundation, thank goodness, realized that that is important. And we aren't the only supercomputing center funded by the National Science Foundation. There's other very good ones. They also do international collaboration. And if you have researchers that already have computational access and use San Diego or Pittsburgh or others already, that's wonderful. I'd love for you to use my computers, but you can work with them too. And we all work together in the US. We compete with each other for the big awards for the systems, but then once that's over, then we help each other. As I said, no charge, right? You get access to our people. You get access to our hardware. And we have software developers that have been building portals, like I'll show you with DesignSafe, which is something we didn't have maybe 10 or 12 years ago. We did not hire a lot of software developers. And now we have about 25 software developers that build out these infrastructures that allow people to access our resources through the web and not have to know command line language to be able to and how to build a batch job, how to log into a system. You don't need to know that. You can focus on your research and access this through various portals. Building the portals is mostly not free. Using them is free. Us building them, if you had a very specialty portal that you wanted to build for your, I think we would need money for that, but most people don't need that. DesignSafe portal. What is DesignSafe? All right, as I've been saying, it's a web-based research platform. All right, it allows, and it's focused on the natural hazards. And again, it allows you to interact with what we call cyber infrastructure, is all of it, right? It's a platform for data sharing and publishing, and that we believe is one of the key aspects of what we do with DesignSafe, is sharing, publishing data, and it's a key aspect of what NSF wanted. What we did on top of that, is the ability to interact with all of that data without having to download it, bring it to your own computer. You can access it, and I'll show you how to do that directly in the web interface. And that's huge. Sometimes it is 500 gigabytes of data, 40 gigabytes of data, a terabyte of data. Well, terabyte of data, you can't download that to your laptop. And also, if you started doing that, it would take weeks through a web interface. So we enable you to do that right in the interface, right in the web interface. Cloud-based tools. And when I say cloud, the cloud is TACC. This isn't a commercial cloud. We are the cloud that I'm talking about, private cloud. And we not only support computation, right, but anything else you can do on a computer, data analysis, visualization, and then our goal, amplify and link the capabilities of natural hazards researchers in the US and abroad. By the way, I stole these slides, most of them, right? Because Professor Ellen Rathje, she's the PI of this project. She's a civil engineer at the University of Texas. I really work for her, and I work for my boss, Dan Stanzione at TACC. I've got two great bosses. So I didn't make this slide and put "and abroad," okay? This slide has been around since 2015, okay, from the very beginning. This is not just because I'm in Italy today. And you used these exact same slides when you worked with us, yes. The program we work under, we are the cyber infrastructure part of this, but at NSF, the program is called NHERI, Natural Hazards Engineering Research Infrastructure, and it is 13 separate awards from the National Science Foundation. It not only funds us in the cyber infrastructure, it funds many other things. There's a group at Berkeley that is building new simulation tools, mainly focused on regional simulation for hazards. They started with earthquake because that was where they most, and actually it's the original developer of OpenSeas, who is still working in that area. His partners have moved on to other things, but Frank McKenna is still doing that work. Greg Fenves was actually the president of the University of Texas for a while, and is still a president of a university over in Georgia now, but he was an original developer back in 1997. But you would think I'm a civil engineer the way I talk. I don't know. I've been with you all for 8 years. But we have a variety of things that are funded in this same program, and we work with all of them. There are experimental facilities, wind tunnels, 2 wind tunnels, a shake table at the University of California, San Diego, the largest outdoor shake table. Other types of there's a centrifuge, mobile field shakers. These things are really neat. Induced seismicity, and they have 6 of these different trucks, and depending on what kind of environment you're in, you can shake the ground, and they put sensors out and then get profiles of the ground. Those are really cool. Professor Ken Stokey at the University of Texas. And they come out and do demonstrations and shake and feet shake. There's a new facility called Niche that's coming online real soon. Full scale testing for community hardening and extreme wind, wave, and surge events. So it's a multidisciplinary because normally wind and storm surge are two separate disciplines, two different sets of researchers, and they're bringing this all together into a single facility. That's a very new award and is coming online soon. So all of their data from those facilities is required to come to us. And we're working on getting the researchers to publish as much of it as they should be. But there are still dozens and dozens of data sets from these facilities available publicly that you can find and use. Because these are one of a kind of experiments. You put a 10-story laminated timber building on the outdoor shake table, you're going to do that once. You're going to shake it until you break it, and then you're actually going to set it on fire and shake it some more and take more tests while it's on fire, and then all of that data ends up there. But you're not going to replicate that experiment. You're not going to also build another 10-story building in the future. That data gets shared through us, and there might be a completely different idea you have on how to analyze that data. And I'll show you in a minute why you could look at that data and actually should be able to understand it. International impact, Margot. I mean, is my prime example, but without her, our ability to have other people use OpenSeas, and she said earlier, you know, she used OpenSeas on our computers. She also then became the teacher for other people. She documented how to do it. She gave examples how to do it. She did a webinar that we recorded how to do it. It's still up on our YouTube channel, and people still look at that for support. And then as people had questions and problems and sent tickets, and then she would get on a Zoom call and help people find their problems. And then when Margot left, we lost a lot of OpenSeas expertise, but we have different people come in, right? Right now, our most recent person that we brought in is an expert with ANSYS, which is a commercial code with a license. We do have some commercial codes available. We do a lot of open source, but we have some commercial codes. And Wenyang Zhang, who also came from UCLA, right? Yeah. He was not at USC. He was at UCLA, right? Yeah. No, I think it was UCLA. He worked with the Berkeley guys too and Stanford. But yeah, but Wenyang is now with us, and his expertise is still there. Wenyang Zhang. Yeah. But we've had international postdocs from around the world. Oftentimes they have come through U.S. universities, but they are international students. But I also wanted to express this to you that we have opportunities for people to come and work with us, and they might work with us 2 or 3 years, and then move on to look for other positions, or maybe go home, and that's great. That's fine. We love it. It's not a problem. I'm not mad that I'm mad you left because I lost your expertise. That's the only reason I'm mad, but I'm super happy for you to be home where you belong. Family is most important thing. But your students, or if you are a student, there are opportunities, and I'll talk a little beyond working for us. There are other opportunities to engage with us that are, I believe, of much value. Okay, just a little commercial. Get a DesignSafe TACC user account. It's free. It doesn't cost anything. And then you can access the tools and you can bring your own data. Without it, you can't get to those portions. You can get to the data, but you only see the publicly available data. We need to know who you are, because you're going to be ultimately, if you interact with the data on our supercomputers, we're required to know who you are. So you can bring your own data. You can use the tools to work on your data and the public data that's available in DesignSafe. Generate new data, right? And the last thing, curate, publish, and receive a citable digital object identifier, DOI, for your data. Other people use your data, they put it in a journal paper and recognize you for your work. Many universities around the world are beginning to recognize that generating reusable data sets have value, and it's valuable for your career. So there used to be journal papers was kind of the only thing to move up academically. We're seeing more and more. I know the University of Washington in particular has done this for a while now in Seattle. But designsafe-ci.org, go and get an account, play around, try it. It's free. Here's what it looks like. This is the front end of the website, and on the left of the navigation is where everything happens. Workspace, I think actually this might be an old image. Huh. I think it now says workspace. Anyway, on the left menu, that's where all the action is. That's where you can interact. But we also have a learning center. This is where you can learn about trainings we have that are upcoming, webinars. And we have people from all over the world that join the webinars. We record them and put them up on YouTube, and you can go to the Learning Center and find out what other things are available there that we've already done. Also, other opportunities to engage with us. I mentioned all the facilities, shake tables, all of that. Those are all found under near facilities. Other community-related things that here. So explore the website and see what's of interest to you. The data depot, as you might think, that's where all the data is stored. The workspace is where is now called tools and applications, because we wanted to be more explicit. It's where all of your tools are to work on your data. The recon portal, reconnaissance portal, is where you'll find field data from. We have links to field data where people have gone out and done, like right now, the big earthquake in Turkey. You go there, there's a map with a point on it, and you click on there and you'll see all the data sets that we currently have, or reports, information we currently have about the Turkey earthquake. But we have events going many years back that you can go and find what data is available, not just in DesignSafe. If we find data other places publicly available, we just link right out to those. User guides are really important. They're written documentation. Please look at them. But you know, we have a ticket system over here under help, and so more often than not, people say, I'm having trouble using this, using that, and then they send us a note, we respond and say, in this part of the user guide. This part here is called impact of data reuse. Over the last few years, we've really focused on providing you with real world examples developed by researchers like yourselves of how to use the different tools in here. And so, because we're computer people, we can build it up, we can provide it, we can make sure it functionally works. But what types of specific applications are out there that resonate with you? We're starting to provide good examples of that from our academic partners. So I said, these are the different aspects of it, as I mentioned. So we have the tools and applications down here, and I'll show a bigger image of that in a minute. The data depot, where you can put different bits of data, different ways to store it. Here's that recon portal. You can look and see, oh, there was an earthquake here, there's an earthquake here, there was a hurricane over in these areas. And then you'll see the data associated. You click on it, the particular event, and you'll see the data files listed. Our data repository recently became Core Trust Seal certified as a trustworthy data repository. This was 2+ years of effort on our part, with one person in particular, Dr. Maria Esteva, our data curator. She did an amazing job. We had to pass a rigid set of standards to be known as a trustworthy data repository, and we are now. Because some people look at us and say, well, are you going to be around? You're your project. You're an NSF project. Why should I publish my data with you? Well, just having DOIs, we're obligated. There's an obligation of, well, if you issue DOIs, there's an obligation to maintain that. But that's not as well known as some things like international certification. And so we just were awarded this, and we're very proud of it and very happy to have it. And it means that you can trust that our data store, our data repository, when you publish your data, it's going to be correct. If somebody goes to get it, it's not going to be damaged in any way. And also that it will be there for a very long time is sort of the core of it. Tools and applications. Numerical simulations. Most of this is relevant to the natural hazards community. AdCirc is storm surge. ANSYS has a variety of physics applications that can, but structural engineering is a big, fair number of structural engineering people use this. Tsunami, ClawPack is a tsunami thing. Dakota is actually an uncertainty quantification tool that a lot of engineering is moving to, especially with performance-based engineering. LS-DYNA is another licensed technology, has some limitations for access, but it is something that we do make available. Actually, ANSYS bought them recently, so this has less limitations than it used to for access. Material point method is becoming a much more popular tool in this area, landslides in particular, and this is a tool that Krishna Kumar at the University of Texas brought to us and is continuing to develop, and it is available to you. Open source tools for CFD, OpenFOAM, and then OpenSeas, and developed here in Italy, STKO version of OpenSeas, which gives you a front end and back end to the OpenSeas framework that makes it easier for you to interact on the front end of developing your inputs and your mesh and all these things to put get your research ready to be run in OpenSeas, and then visualization and data analysis capabilities on the back end. And we've been working with Massimo and Guido for a number of years now, and we've had this available in the interface for quite a long time. And again, open to the entire world research community. Okay, Jupyter has become such a big deal in the you know, you look at these other areas up here, and I'll mention like data analysis. We also offer MATLAB. It used to be we could not offer MATLAB except to our University of Texas staff and students, because MathWorks, the company that licenses MATLAB, we have an agreement with your university, and only your university can use it. That's the license. Well, Jupyter comes along, open source. Python is very easy to learn, and a lot of what you can do, and now there's so many libraries and add-ons for Jupyter, they can kind of pretty much replace MATLAB, and it's free. It's open source. There's no license needed. Suddenly, we're able to, several years ago, suddenly add MathWorks to anybody, or MATLAB, anybody that wants to use it. So imagine that. Yes. So visualization. I don't have pictures of all this stuff, but we have lots of visualization tools, including GIS types of tools. One we develop in-house called HasMapper, and another one, QGIS, is a very common open source tool that everybody can use. We have that directly here. And the thing is, when you run these tools, you don't have to download the data. You can run these tools right here, access data that's in DesignSafe that either you brought, and there's really no limitations to what data you bring to us, and access to the published data and publicly available data that's in here. Go explore and see what you can find. The Sim Center at Berkeley, mentioned Frank McKenna earlier, they have developed a number of regional simulation tools, and a lot of it is based on uncertainty quantification. Actually, if you go to the OpenSeas wiki, there is actually a presentation about the Sim Center, and he talks extensively about uncertainty quantification and why just running the tools like OpenSeas without doing uncertainty quantification gives you an answer that is kind of meaningless unless you know what are the bounds on that, right? What's the lower bound, upper bound, right? Performance-based engineering, we have to know how is that going to perform under variations of the forces that are being experienced. And again, Jupyter Notebooks. Jupyter Hub. We run a Jupyter Hub. We actually run what's called Jupyter Lab. We run it in something called Kubernetes. It runs in the cloud at TACC. What that means is if we get more and more people using it, Kubernetes automatically builds another VM and starts more capacity so that more users can keep going. So we're limited by a certain amount of hardware. At some point, it won't be able to build anymore, but you can use this. You can use this to teach your classes. Students don't have to build get Anaconda and build everything on their laptop and become their own system administrator on their laptop. If the Jupyter notebooks are in DesignSafe, and we have a lot of people that teach their classes, they're developing classes in Jupyter notebooks, homeworks in Jupyter notebooks, and it's a great way to get your students to learn computational techniques in a way that, well, you kind of have to if you want to turn in the homework. But really, there's so much value in that, and every conference I go to anymore, even a lot of the professional engineering firms are starting to say, we've embraced Python. We need more computation. It's more than Excel spreadsheets anymore, right? So I think it's very valuable for the students to learn. And you can publish Jupyter Notebook. It's a file. The Jupyter Notebook is a file when you get right down to it, right? And so I'll show you something about publishing here. Okay, here's the data depot. What time is it? We okay? All right. Okay. There's the boss. All right, we're okay. All right, so here's what the data depot looks like. You'll see on the far left, I show that we've got private data areas and public data areas. So if you're not logged in, anyone can see what we call published. That's since we took over 8 years ago and created this newer, more capable publication capabilities. Published NEAS, the previous project before NEARI DesignSafe was called NEES, and it was around for 15 years. It was the Network for Earthquake Engineering Simulation. They did publish data for a while, and we have all of that data. Once you get a DOI, data never goes away. We inherited it. We keep it going. And then we have something called community data, which is an area for public data that's not curated. Up above, what we call private data. As a user, you'll get a space for your data called My Data. It is actually a directory for you on the Cockerill storage system, the 50 petabyte storage system. My Projects is a private area for you can create a project, and it's a shared space. Think of it as a shared file directory. So your research group, you could start something called, My Research Group, add a project. These are all projects over here. And then you can add members of your research. They all have to have DesignSafe accounts, but then you can add them to that. And that's the only people that can see all the data that's brought there, but everybody can see all the data that's there. Everybody can contribute to the data that's there. Everybody can work with the data that's there. And it's the place where you start if you want to publish data, is from within a project. I'm on a project with Margot here. All right, machine learning models. Oh yeah, that was kind of an important one, wasn't it? All right. So if you're going to publish, you have to start in My Projects. You go through a curation process, and it's somewhat structured, but flexible. So Dr. Maria Esteva, Dr. Esteva is a librarian. She's a digital archivist. She is a librarian, trained librarian, PhD. She worked with the community and said, talk to me about your research. Let's find commonalities. The experimental project data model, she built data models around each of these that had common lingo, common language, and an ontology, a structure that made sense. This experimental project data model works whether it's a wind tunnel, a centrifuge, right? A wave station, any of the above, the shaker trucks. Numerical simulation model, hybrid simulation, if you're doing a combination of doing an experiment on a shake table, for instance, and part of it is being modeled. You take the outputs of the sensors and put it through over to the computer, and you're modeling 3 more stories that aren't actually part of the structure, and then you feed that back, and then you shake it again and do hybrid simulation. Field reconnaissance, work done observationally, and we also now have social sciences as part of this as well. So social science data in here, as well as engineering data and field reconnaissance work. We have a separate data model for that. And then we have other. Maybe it doesn't fit. Maybe it's a simple report, not complex at all. All you need is a title, and there's minimum metadata involved in these, minimum descriptions, metadata. Metadata is information that describes your data. The other just needs your names, you know, the authors and a title and your institution. With flexibility, right, comes great responsibility. So you remember that you're publishing your data just like you're publishing a journal article. What you put out there, the quality of it and the likelihood of it being reused is how much effort you put into thinking about it and putting it out there in a way that other people can reuse it. This is what a published data set looks like. It kind of looks like a journal paper, right? It's got a title, it's got the authors. We tell you what kind of data it is. This is an experimental project. Here's your DOIs, some keywords, the abstract. We have a data diagram that just a visual view of what happened. Now, if you're someone who has, let's see, what did they do this on the centrifuge? Yeah, right here, Center for Geotechnical Modeling. You say there's centrifuge. If you looked through this, this would make a lot of sense to you. If you were somebody who did soil structure interaction work and looked at this kind of data, and there's requirements on including the sensors, and then you shook it this way and you shook it that way. It's all that information is there. You can download the entire data set. It's okay to download it. You don't, if that's what you want to do, you can download the data. We don't prevent you from doing that. And then you can view data metrics. You can see how many people have downloaded that data ahead of you. If you're the author, it's nice to see how many people have downloaded that data and used that data. But make your data count. When you're building this out, make sure that you're doing it in a way that other people can reuse it. And then other people, you know, we want them to cite it. Well, we make it easy. Just click on the blue citation button, and here's the proper citation. They can just copy and paste that or hit download, and it comes down as a little text file, and they can put that in the references of their paper. There we go. Reuse, reduce, recycle, right? Make your research reproducible and reusable. Okay, you will get a digital object identifier. It's not a URL, it links to a URL, but it's more than a URL. It's persistent, it's forever. Okay, and put that citation in your reference list. Many journals are finally allowing you to do that. In the beginning, they weren't. They'd say, oh, put it in the acknowledgements. That's not a journal article. You can't put that as a citation, but it's getting a lot better now that it's being accepted. And a lot of journals now require you to publish your data along with that. You have to have a DOI somewhere where people can access your data. So how do you curate data? What's that even mean, right? We help you. Again, it's our people. We have written documentation. The user guides are there. You can go through and read about it. And we have people that do that, and they publish just fine. They never need to contact us. It works great. But we have virtual office hours, and you will get Dr. Maria Esteva to help you, who designed all of these things. And she makes herself available Tuesdays and Thursdays, twice a week, okay? And if that doesn't work for you, she'll coordinate another time, okay? And sometimes she's back home in Argentina, right? And that's fine. That gets her in a different time zone. It's even more helpful. So, so we have lots of support and lots of help, even for curating your data and publishing your data. I need to update this because Joe Van Tassel no longer works with us, and neither does Mahyar. But I said we had global outreach. Mahyar was from Iran, and he worked with us. And Wen Yang's from China, he works with us, right? Margot from Italy. Joe was just a regular U.S. guy. He's now a professor at Virginia Tech. We're okay with people graduating from us and becoming more successful. I mentioned the use cases. Real world examples of people using the infrastructure, many times having Jupyter notebooks because they're so nice for teaching you, right? You can document the workflow. and describe what you're actually doing and not just share the code, right? Well, here's the code over here. You can go find the code. No, it's right in the notebook, right? You can see the code that's being executed. You hit a button and the code runs, but there's some text right next to it that you can add, and it's very nice. So we have geohazard, general geohazard use cases, hurricanes, windstorms, seismic, all kinds of use cases available to you. And then I think this is my last slide. International reach. There are multiple ways to get access to our resources. So the portals like DesignSafe are a fast, easy way and fairly unrestricted. Where we restrict it is you might not be able to get, if your job needs 100 nodes of Frontera, we aren't going to give you 100 nodes. We can actually restrict the usage through the web, which is good. We keep within the regulations bound to the US government that way. So, well, you get 4 nodes or 8 nodes with, smaller amounts. But most research in this area doesn't need more than that. That's hundreds and hundreds of processing cores. And it's a great way to start. Maybe it's all you need. If you find you need more control and more capability, we're required to have a US PI be the lead of a project. And like you're working with Scott Brandenburg from UCLA right now. Scott is the PI on a project. Margot has an allocation on Frontera. They work together. They wrote a small proposal, just a few pages, to say, here's what we're going to do. And then I give them time on the system. Okay. And they have a lot of time on the system. And then if you don't have close US collaborators, reach out to us, ask us. We can. I work with thousands of researchers. I travel. This is what I do. I travel. My wife kind of hates it, but she's here this time though. She doesn't hate it so much. First time to Italy. It's wonderful. So, but I travel a lot. I know a lot of researchers. My job is to help people collaborate, help you get your research done, help other people collaborate. I'm happy to help. I know what other people are doing around the country, around the world, doing similar work, and maybe want to work together. I mean, you do too, right? You go to conferences, you write papers, you read papers, all that. If you want help with some introductions that you think you're having trouble getting, I might be able to break through because they use my computers and they want to keep me happy. Webinar trainings and archive trainings. We have YouTube channels. And we're in the process on the TACC YouTube of developing very short 2-3 minute videos. That's where this generation is. We're trying to meet you where you are, right? My kids are this age, kind of. So I know that we need to not put a 4-hour webinar up and expect anybody to look at that unless you're really, really intense and need this to get your thesis done. We need 100 short videos, not one 8-hour video. Okay. And we're building a lot of that out. And some of it's very simple. How do I log into an HPC system? Literally, that's the video. We have, in addition to our online, we have in-person week-long in the summer that if you have the means to travel to the US and spend the week, you can have immersive, in-depth training on parallel programming, scientific visualization, machine learning, and we do these every summer. During the regular semester, we do 4-hour, 8-hour trainings on the same topics. They're just short, more abbreviated, give you more of an introduction. Again, get that account. You'll also be invited to our Slack team. So if you've used Slack, you know what it's about. If you haven't, it's kind of like it's a great communication center to communicate with other people from around the world. We have over 7,000 people who have accounts. Okay, you're going to be connected to people around the world. You can direct message me, right? Okay, my phone beeps. I'm here. What do you want? And we have dedicated channels for various topics, but also as soon as the Turkey earthquake hit, we created the 2023 Turkey earthquake channel. People are talking when there's a hurricane in the United States, people get on there and start planning. Where should we go? Where's it going to land? We should set up, because they set up instrumentation to record wind speeds, barometric pressures, water heights, all kinds of, for the storm surge, and they talk to each other. Where can we stay? Oh, these hotels are for the local residents. Don't use them. It's not fair. It's not right. Okay, we're going to stay over here. It's amazing to watch the NOAA hurricane planes, the planes that fly through the center. A few years ago, those people joined our Slack and started talking. So we get those people telling us when they're going to fly, where they've flown through. It's amazing. It's incredible. You're sort of part of the reconnaissance efforts that are going on. It's really fascinating. So I encourage you to be a part of us, and I think you'll get something out of it. And then if you need even more, reach out. Thank you.
Thank you, Tim, for the very interesting presentation. So I would like to check if there are questions. Let's check via web. If you have any question, you can just raise your hand using the tool. Or in the meantime, if we have questions from the floor here, please just, you can come here and ask the question. Yes.
So the question is, do we handle sensitive data at TACC, and how do we deal with that, right? And how do you deal with publishing that in particular? So that's really interesting, and that's a great question. And it is, the short answer is yes, we do that. Several years ago, actually, when I first started at TACC, I actually worked on the project for us to go through the documentation, create the documentation to handle what we call protected data. And there are many, in the US, there are many regulations around, depending on if it's health related, education related, et cetera, right? So we did that. We've passed audits, and we are fully compliant with US regulations around that. And we believe, we do look at GDPR, and we do our best to be compliant with that. And we have a compliance team. Again, we're a very large organization. We have a compliance team that if you had questions about the regulations in various other countries, or just or just GDPR, how do we relate to that in a particular use case, we have people that I can direct you to answer that. So the way we typically do this is, you can bring sensitive data to us if you need to calculate, do some analysis on that. And we have a special encrypted file system where we keep it. We also, you can bring it to the supercomputer to run, but what we do is you run through a special login node, and that data goes through an encrypted file system that we spin up when you ask the data to be started and run on the system. And then we burn that down at the end of your job, and we wipe everything. So it's a fully encrypted network channel that we build up just for your, and if there are 5 or 6 of you doing all this, we build, each of you gets a separate file system, right, that is fully encrypted. Yeah. So yes, we handle that. Now, how do you publish? So what I see through DesignSafe so far is mainly personally identifiable information that has to do with social science research, right? Because when you're out asking people questions about how they felt during the earthquake and their health and things like that, they have all the individual data files, right? But then they have to use some kind of statistical analysis package like R or Stata or something like that, or SAS, and they're trying to do different analyses on that. That raw data is protected, and they cannot publish that data. They can publish the outcomes because the outcomes are not about they're broad aggregated outcomes. So what they will typically do is publish the instrument by which they collected the data. So if it was a survey that they sent out electronically, you'll see all the questions they asked. They'll publish that. They will publish some outcomes that they learned from it. And then they have a note in their published project that said, if you would like access to the raw data, contact so-and-so, right? Because they have to go through a process of what are you going to use that data for? They have to write a little proposal, right? And then your university that has to let them become a member of that. I don't know what they call it here, but we have an institutional review board in the US, IRB, similar. I'm sure there's something very similar or identical here. And that the university has to approve that, and all the proper paperwork has to be in place. So they just include that in what they publish is contact this person who is authorized to work with you to get access to that data, the actual raw data.
We have one more question.
Okay. In my past experience, I've been used to work with the climate models, which require long time simulations. That's interesting. We are right now introducing to Dakota, and we are using it as for parameter estimations.
Yep.
It means that you have to run the same model several times.
Yes.
Each time you finish run, or you are not allowed to run the same model for more than X days, let's say, you need a restart and so on.
Yes.
In my experience, a word I learned to hate, that is Q, because we're obliged to wait sometimes for the same time of the simulations. So my question is, how is really currently busy the system?
Yeah, that's a great question. Yeah. As with any high performance computer, right? There are never enough of them. The National Science Foundation could give us 5 times the money, and it's not enough. So our systems, 90% of the time on our systems, the computing time, is allocated nationally, because there are many computers around the country funded by the National Science Foundation. And there's a central organization, and we're all part of that, right? We go to all the meetings. I see everything that happens. I can read all the proposals for time. But we have peer review, right? Other professors, other researchers around the country review each other's proposals, right? And we do this quarterly. And the quarter that you put your proposal in, you can't review any proposals, right? So that's conflict of interest. So, but on TACC systems, Stampede 2 in particular, that's been around for a while now and is still the biggest system for accessing on the national. Frontera is allocated separately by us. We were typically 8 times over requested. So if we had 9 million compute hours available that quarter, 72 million hours were requested. Okay. Some projects immediately get rejected by the reviewers because they're just terrible proposals. Others are very experienced people that have been doing this for 15, 20 years, and they write a bad proposal. They copied and pasted last year's proposal. They get caught. You can't mail it in. You can't cheat, right? So you got to put some effort in. You got to write a good proposal. 8 times over requested, usually after the reviewers were done, we were still 3 or 4 times over recommended for the amount we had available. There weren't enough other systems. Other systems got requested, but usually they had a little time, and we could move some of that over. But there's still time that we just had to reduce everyone's amount of allocation. And the National Science Foundation just doesn't have enough money to provide enough. So what does that mean? We try not to over allocate the systems too much, but we always, if I have 9 million available of theoretical time available, I will usually go 9.5 million, 9.8 million awarded, because not everybody uses their time and other people need a little more. And they'll come back in the middle of their time. They get it for a year. They get that time for a year, and they'll need more time. Sometimes lots of people do use a lot of their time. There'll be periods right before a conference submissions are due, things like that. You'll see very busy times. You could wait 4 days. Yes, you could wait 3 or 4 days for your job to start. This is why you need to plan a research campaign. You plan 20 jobs, and you put all 20 jobs, submit all 20 jobs. Sometimes they'll run right after another. Other times 10 of them will run, and then you have to wait 3 days for others to run, right? So we try and encourage people to think ahead as much as possible, plan ahead, and submit lots of these jobs. Also, you're correct, we have a 48-hour maximum runtime. So you do have to do what we call checkpoint restart, right? You have a file, checkpoint file, that grabs all that data, and it's the starting point for your next time. And you might run a 48-hour job. Astrophysicists, high energy particle physicists, they all run these jobs. Sometimes they last months. They run 2 days at a time, 2 days at a time, sometimes on 1,000 nodes, 2,000 nodes. And then they might not run for a week because their priority dropped. They ran too much and new people came in. They run first. And then all of a sudden their jobs start again, but it's automatic. That file's ready and it starts again. They know that they have months to deal with, and so an extra few weeks doesn't hurt them, right? So you, on Frontera, usually it's no more than 2 days wait. Small jobs, those get run really fast on Frontera, because when I've got 2,000 nodes that somebody's going to use, I need to drain those down to 0, no use, to be able to put a 2,000 node job in and have it run. Well, I might start to drain some nodes down, and I drain down 64 nodes, and then another 128, and then but these other ones are going to take 8 hours before they're all going to be drained. As long as you provide a maximum runtime for your job and it's less than that amount of time and it fits in that space, we'll put it in there. We run at 98% utilization. Any given 24-hour period, out of those 8,360 nodes, only 2% of the overall, in a 24-hour period, only 2% of the time gets wasted, because our scheduler is smart enough, and we tune it, and we it's all, it's automated, but it's got parameter settings, and we can keep those nodes full to within 2% of unused time in any given 24-hour period. It's pretty amazing. So we're glad to have 1 node jobs, 2 node jobs, 8 node jobs. We're happy to have them, because the $60 million computer doesn't sit around doing nothing while we're waiting for a 2,000 node job to start. So Frontera, you're going to run a lot faster on, because we control that entirely. Stampede 2 is on the national, Frontera is nationally available, but we control the processes on it. Stampede 2 is allocated by mostly by a national committee. We're a part of that. I can influence it, but I have much more control on Frontera.
So I've seen that you are expanding your GPU power, or at least that's the intention. Now in Europe, recently there's been quite some hype in trying to get some these QPU quantum accelerators. I want to know if TACC has any plan on that.
So we are very closely watching the quantum. We had actually one person on our team who had a background and he got his PhD studying quantum computing. We think it's pretty far off for us to have any capability there. We have to provide something that can be 98% utilized. We have to provide something that has to have at least 95% uptime. So available 95% of the time, and of that 95% availability, we have to be 98% utilized. We have to support production science. So we have to do that with the most cutting edge technology that can be reliable. And so while we are working with people that are doing quantum, I don't see us doing anything for quite some time in terms of making it available more broadly. Yeah. Yeah.
Okay, thank you. If we don't have any other question, I would like to thank you again, Tim, for being here for the great presentation. It was a pleasure, as always. And I would like to thank everyone that was here today, here in presence or connected. And I hope to see you all next time. Thank you.